In the previous video, we defined the potential energy, I should say the electrostatic potential energy between 2-point charges as the integral from going from R1 to R2 of F dot dl, where F is the force between those two charges and R1 is the initial position of any one charge, and then these two charges, let's say this is Q1, Q2. This one is fixed, or you could say that this one is fixed. It doesn't matter. But if one is fixed, then if the initial position is R1 and the final position is, let's say, R2, and it goes in some crazy path, and there comes Q2, and we go in that direction, then we see that the potential difference, the change in potential energy between the initial configuration of the charges, which is this, and the final configuration of the charges, which can be expressed in other words like U at R2 minus U at R1, is the integral of from R1 to R2 of F dot dl. Now, there's something called the potential difference, which is very closely related to potential energy. It is defined to be delta V, and this looks almost the same, but it is defined to be the integral from let me use A and B, from A to B of E dot dl. So and this can also be written as V at A minus V at B. So this is very closely related to potential energy. Here we have the integral of F dot dl. So if I write what is F is K Q1 Q2 over some R squared, right? Some R squared. And what is E? E is just almost looks the same, but we just have Q1 there, right? This is the field due to Q1 at any point R. So it looks like we got from here to here by just dividing by the charge, right? We divided both sides by Q2, and we got from F we got to E. So I guess that on the left hand side we must have done a similar thing. We must have divided the potential energy by Q by some charge, and we must have got this term here, and that is indeed the case. We now know that the potential energy divided by the charge is the potential difference, or I should say the difference in potential energy divided by Q is equal to delta V. So you can rearrange and you can get a term here, and that is Q delta V. So this is kind of a thing to memorize, but you get used to it. No need to memorize too much. So that is the definition of potential difference, all right? So these definitions are very important because many questions involve are very tricky, which require a very deep understanding of the definition of these quantities. So I believe that that is enough for the definitions, and now let's see how we can calculate electric fields and electric potential difference, or I should say electric potentials, if we define. And then I forgot to mention one thing, that as the potential difference is V2 minus V1, right? Delta V is V2 minus V1, but if the initial R1 is infinity, which implies that this charge Q2 was at first initially it was infinitely far, and if R2 is, let's say, R, then by definition the potential at infinity is defined to be 0. That is a convention. You could call anyone 0, but it's kind of helps a lot. So and v at 2 we can just call as v. So this implies that the thing can just be, the potential can just be defined to be kq over r. Okay, so this is kind of the definition of potential only when you choose the reference as infinity. Yeah, I guess that's pretty much it for the potentials and all the definitions. So now we'll look at how we can calculate electric fields and electric potentials for different charge distributions, like a rod or a ring or a disc or a sphere or a hollow sphere or any kind of shape. We can calculate the potentials at different points as well as the electric fields at different points. So that is kind of the application of these definitions. So that is more important than these definitions, but I believe that we cannot get to the application until and unless we do the definitions. So just kind of to make things a bit more easier, I'll use some of the more standard definitions that I'll for calculating potentials. I'll assume that we choose the reference as infinity. I will not tell you that it is, but it's kind of assumed to be that. So yeah, that's pretty much it, and I'll see you in the next video.